Hello everyone and welcome to this presentation. My name is Amir of Audio Analysis Lab at Aalborg University in Denmark, and today I want to present a speech enhancement technique which is based on classification of noisy signals decomposed using NMF and Wiener filtering. This presentation has been presented originally at EUSIPCO 2018 in Rome. So after introduction and problem formulation, I introduce a proposed method and explain the experimental setup and discuss about the results and end my presentation with some conclusions. A major challenge in existing speech enhancement techniques is to accurately estimate the noise statistics, particularly in non-stationary environments. The classical estimators are typically based on voice activity detectors or on tracking the non-stationarity in short segments of the signal, but they are less accurate when tracking highly non-stationary noise with low signal-to-noise ratio. The methods based on time frequency analysis, on the other hand, don't require estimation of noise statistics. Methods such as empirical mode decomposition decompose the noisy speech signal into components. Then the less corrupted components are used to reconstruct the enhanced speech signal. Recently, speech enhancement techniques using non-negative matrix factorization have been proposed, which are based on training the spectral diversity of speech and noise from relevant training data. Non-negative matrix factorization, or NMF in short, is an unsupervised approach for linear representation of the data. In this framework, a matrix of observation V of size f by L is approximated by a basis matrix W of size f by K and an activation matrix of size K by L, and all elements of these matrices are non-negative. In order to use non-negative matrix factorization for speech enhancement, the observation model in time domain is typically assumed to be the summation of speech and noise, and by a non-negative transformation we can have a spectral power matrix. Then this matrix can be decomposed into spectral basis matrix and temporal activation matrix. We can do the same for speech signal and also the noise signal. Matrices W and H are estimated by minimization of a cost function, which is a kind of divergence subject to the constraints that all elements of these matrices should be non-negative. And then these matrices are updated using a multiplicative update algorithm using these two equations, and in these equations the multiplication, division, and power all are element-wise operators. Speech enhancement techniques based on supervised NMF consist of two phases. During the training phase, spectral basis vectors describing noise and speech in the noisy observation are independently trained using the relevant training data, and during the enhancement, the temporal activation vectors of speech and noise are estimated using the spectral power matrix of a noisy observation. Then these matrices are used to calculate the Wiener gain to be used for estimation of the enhanced signal using the noisy observation. But we will show that the enhancement quality reduces when the basis matrices are trained on data that is not highly relevant to a speech signal and a noise signal in a noisy observation. To tackle this problem, instead of training the basis matrix, we propose to decompose noisy signal into less overlapping parts by applying NMF followed by Wiener filtering. Then by applying a classifier, we can identify the less corrupted parts, and the enhanced signal is the combination of these less corrupted parts in time domain. So in this case, the observation model in time domain is the summation of speech and noise, and the observation signal can be represented in the time domain by the sum of k parts. And due to the linearity of the STFT, the signal model in time frequency domain can also be represented by the sum of k parts. And we assume that parts of the speech signal and parts of the noise signal in the noisy observation are less overlapping. In this sense, each part can be classified as part of either speech or noise. Then the enhanced signal is reconstructed by a combination of parts of the noisy observation which are classified as a speech. So we use NMF to factorize the spectral power matrices of training speech signal, training noise signal, and also testing noisy signal. Then the filter banks of spectro-temporal Wiener gains for each signal are obtained as follows, in which the GKs are the gains for each signal part. Then each signal is decomposed into non-overlapping parts using its corresponding filter bank, and applying an inverse STFT transformation, we can obtain signal parts in time domain. Let's take a look at the speech signal, the noise signal, and also the noisy signal, which is a combination of these two signals, and also the decomposition of these signals into 5 parts. If we focus on the parts of noisy speech signal, we can observe that these two parts are similar to the parts of speech, and these 3 parts are similar to the parts of noise. Now we should discriminate between these parts. To do so, we use a classifier, and for training classifier we need some features. We have shown in our previous work that the distribution of MFCCs is predictably influenced by additive noise. So we use the property of these features to distinguish between speech and noise. So the proposed method consists of 2 phases. So during the training phase, the training speech and training noise signals are decomposed into signal parts, and then the signal parts are segmented into short frames, and for each frame, MFCC features are extracted, and features are averaged over frames to have 1 feature vector per each signal part. And then features of signal parts and features of the noise parts are used to train the classifier. During the enhancement phase, the noisy observation is decomposed into signal parts, and we calculate the features from those signal parts, and the parts are classified using the trained SVM. And once all parts of the noisy observation are classified, the parts detected as speech parts are combined in time domain to reconstruct the enhanced signal. In order to evaluate the proposed method, we use 25 utterances from Noise's datasets uttered by 5 English speakers, and we use 4 different non-stationary noise: train, bird, restaurant, and keyboard. And we consider 2 different scenarios. In the first scenario, the utterances of the target speaker and the signal of the target noise in the noisy signal under the testing were included in the training data, and in the second scenario, those signals are excluded from the training data, to see how the proposed method can generalize the problem. Here we can see the enhancement results average over 100 noisy utterances in terms of output signal to distortion ratio, and also the output PESC as a function of K, the number of signal parts, and input signal to noise ratio. And the dotted line in the bottom plot indicates the input PESC. The supervised NMF method, which is our baseline method, is shown in yellow bar, and the proposed method is shown in red bars. And here we consider the first scenario in which the target noise and the utterances of the speaker under the test is also included in training data. We can see that both methods can improve the quality of signal, both in terms of output STR and output PESC, but we can observe that the supervised NMF provides better performance compared with the proposed method in terms of the output STR. when the utterances of a target speaker and the signal of target noise are included in the training data. However, the proposed method provides an enhanced speech signal with comparable or slightly better quality according to the output PESC values. Now let's consider the second scenario in which the target noise and also the utterances of the target signal, target speaker, are excluded from the training data. In this case, the supervised NMF as the baseline is shown in green bars and the proposed method is shown in blue bars. Here we observe that the performance of the supervised NMF is degraded. This is probably because the training data could not provide spectral basis vectors describing well the speech and noise signals in the noisy signal for the good reconstruction of the enhanced speech signal. But we observed that the proposed method can better generalize the problem. This is due to the fact that different noise types with similar characteristics have similar impact on the distribution of the MFCCs of a speech signal, and it suggests that the proposed method can generalize for unseen noise types if they have similar characteristics and not necessarily the same noise signal to those present in the training data. Now let's listen to some audio files. The first signal that you will listen is the noisy signal at 0 dB. The noise type is bird.
The birch canoe slid on the smooth planks. He knew the skill of the great young actress.
And the second signal is the enhanced signal using the supervised NMF.
The birch canoe slid on the smooth planks. He knew the skill of the great young actress.
And the next one is the enhanced signal using the proposed method.
The birch canoe slid on the smooth planks. He knew the skill of the great young actress.
We can clearly observe that there is no bird sound in the signal. Now let's consider another type of noise, which is a restaurant noise added to the speech signal at 0 dB.
Hurdled a pit with the aid of a long pole. The sky that morning was clear and...
Now let's listen to the enhanced signal using the supervised NMF.
Hurdled a pit with the aid of a long pole. The sky that morning was clear and...
Now let's listen to the enhanced signal using the proposed method.
Hurdled a pit with the aid of a long pole. The sky that morning was clear and...
Well, in this presentation, we propose a single-channel speech enhancement method for suppressing non-stationary noise in a noisy speech signal. And we showed that the performance of the supervised NMF-based speech enhancement is limited when the training set does not contain data that is relevant to a noisy observation. And to tackle this problem, we propose to use the unsupervised NMF followed by Wiener filtering to decompose the noisy speech signal into less overlapping parts, and applying a machine learning technique on top of the algorithm to identify less corrupted parts. And the experimental results showed that the proposed method can better generalize when the signals of the target noise and the speakers are not included in the training data. And thank you very much for your attention.